Right. So, thank you for the invitation. I'm glad to be here. See so many known faces. That's a privilege of old age. So let us start. So this is a report on the work I did with Elena Perutka. But the first part will be I'll set up the situation. So I'll tell you about. There will be three parts. Right away, there will be three parts. The first part I recall things about rational varieties, stable rational varieties, and the like. The second part I will explain how by using unmodified cohomology when tried to show that some varieties are not stably rational. And the third part will be devoted to the work with Elena Perutka. Okay, so rationality, stable rationality, unirationality. So take any reducible variety, reduced over the complex dimension D. When it says that X is rational, if it's birational to projective space PD. This implies that it is stably rational. That is, you can, if you take X and multiply by some projective space, you get something birational to projective space. This, in its turn, implies retract rationality, which is a notion which is not so well known, which was invented by Saltman, and which is really quite nice. So you say that a variety is retract rational if you can find an open set. There's a pointer? No, okay, right. If you can find an open set of the variety such that identity on the open set factorizes through an open set of affine space. So typically if something is stably rational, it is retract rational. Then in its turn, this property of course implies that unirationality, you see I have something dominant here. Unirationality means there's a dominant map from projective space to a rational map to your variety. And then it implies a rationally connectedness, which is a property that through any 2 points, so let's stick to smooth projective varieties of a complex. Through any 2 points, you can find a curve at genus 0 passing through these 2 points. Okay, examples, and this is a not trivial example, final varieties are rationally connected. So typically hypersurfaces of degree D in Pn, where n is at least d. Okay, for d equals 1 and d equals 2, it's well known that all these properties are equivalent. And so the situation changes as soon as your dimension is at least 3. This is a well-known story, but I recall it for a few people in the room who have not heard it. So in 1972, Clements and Griffiths showed that the smooth cubic hypersurface in P4, any smooth cubic hypersurface in P4 is not rational. And the method they used was the intermediate Jacobian and prim varieties, which had been developed by Mumford. And it's a subtle invariant with the dimension of the singularity locus of the theta divisor, which was explained in the Bourbaki seminar some time ago. Okay, but that method completely leaves open the question of stable rationality. Then at the same time, there was this Kovsky-Manin proof that quartic hypersurfaces in P4 are not rational. And what they proved was they developed a method which went back to Max Noether, the fact that the Kremener group is generated by inversions, linear system with the base points. They developed that in dimension 3, and they proved that any birational automorphism of such a quartic smooth quartic hypersurface is an automorphism. And therefore, the birational automorphism group is finite. Certainly, this prevents it from being birational to projective space. But again, this left open the question of stable rationality. And then there was the Artin method, which looked very special. They produced a very specific double cover of P3, ramifying along a certain singular quartic surface. And well, I can show it's unirational. And their invariant was the torsion in the third integral Betti group, H3X set. Now, this is a topological point of view, so to say. And in fact, Dehling in his talk at the Bourbaki seminar explains why this is a birational invariant. You can also view it, if you're more of an algebraist, as the fact that the bar group of the smooth projective model is not 0. Now, the advantage of this method, in this case, the fact that the problem is non-trivial implies that X is not fully rational. It even implies that it's not retract rational. So, I mean, there's been the idea for some time to try to find other invariants that might do the same job. Okay, so between these various properties I listed, there are, you can ask, you know, A implies B implies C implies D. Can we go backwards? So, rational is not stably rational. I proved this with Beauville, Sansuc, and Swindler some time ago. And the method for non-rationality is the Clemens-Griffiths, Mumford-Beauville method. Beauville refined it in this setup where the examples were produced. The Rammstein locus was quite complicated. And so it was the Beauville refinement that enabled us to show that the thing was not rational. Then there's a question which hasn't been much investigated, whether stably rational is the same as retract rational. And I think no one has any idea. Then retract rational is not unirational. This is proved by the power group or the Artin-Mumford method. And there's a question which I will not address, whether unirational is the same as rationally connected. Okay, let's look for a bit at smooth cubic hypersurfaces. So they're all unirational. The Artin-Mumford invariant in dimension at least 4. I mean, X is of dimension at least 3. The Artin-Mumford invariant says nothing. For n equals 4, they're never rational. I just say that. And then there's the open question is, are all stably rational? That's a big open question. Yes? Sure?
What happens if you let n get larger and larger? Does it get better and better? Or you know?
I think we don't know. We don't know. This is incredible.
Okay.
No, the only thing we know is that, so when you're in even dimension for cubic hypersurfaces, there are very classical and easy examples where they are rational. So there's example. I mean, I can tell you examples. For cubic surfaces, you prove they're rational because you find two skew lines, and then you can write down cubic hypersurfaces in even dimension where you find two skew linear spaces of the proper dimension, and you just copy the argument. But in dimension, so this is what I was saying here, is that for n equals 5, Hassett found many other examples of rational cubic hypersurfaces. Yeah. Okay, and for quartic hypersurfaces, so I just say that, I repeat, Skowski-Meinin showed they're never rational. The Artin-Mumford invariant tells us nothing. And so we can ask, is this stably rational? Okay, so I reached section 2. So I want to discuss some stable birational invariants beyond the power group. So the basic stable birational invariant is the Chow group of 0 cycles over a field. Okay, so K is a field, any field, and X is smooth, projective, irreducible. If it is retract rational, then for any field extension, F over K, the degree map on the Chow group of 0 cycles to Z is an isomorphism. And if that's the case, we say that X is universal CH0 trivial. Now, I'm going to indulge in the proof of this because it's not a complicated result. So we have our X, which contains an open set U, and U factorizes through V, and the identity on U factorizes through an open set of projective space. Let's put the right projective space here. And now I'm over a field K, arbitrary field K, and I take a 0 cycle. Now a lemma which has been constantly rediscovered is that it's very easy to move around 0 cycles. So I won't explain the proof. But, so if I take a 0 cycle on X, it is rationally equivalent to a 0 cycle supported on U. So Z in Z0 of X is rationally equivalent to Z1, which is the support of Z1 being U. So you take your Z1 and you push it to Z2 here. Of course, you would get Z1 if you came back. And now you're in this open set V of projective space. And now I say that it is obvious that this Z2 is rationally equivalent to 0 on projective space. Okay, in fact, the point is this reduces to to the only thing I have to prove by going over to some field extension is that if I take two rational points P and Q, now I take them rational in V of K, then phi of P is rational equivalent to phi of Q. And this is clear because I have two rational points in V, they're in projective space. I just draw the line through these 2 points. And then I should say this is in X, this is over X. So U is in X. So this line, which lies in P1K, this extends the morphism from P1K to X. Okay, and so P and Q are rational equivalent, and that's the end. Okay, this notion of being universally trivial has been considered by Markoviev. I'll come back to this in a minute. And also in the paper with Aul and Paramala, we made a survey about this. Okay. So the point is that even when K, the ground field is C, it is interesting to look at this invariant for arbitrary fields. And of course, the obvious arbitrary field you want to use in that case is the function field of the variety itself. Okay, so let's take the complex field. Now this notion of universally trivial has to do with things which have been investigated by many people, and in particular by Bloch and Srinivas in 1983. So they investigated the consequences for the variety X of the fact that the Chow group of zero cycles is Z over an arbitrary algebraically closed field. Not any field, but algebraically closed field, but any big algebraically closed field containing ground field. And then there's a translation of this in terms of the diagonal. So you consider diagonal in X cross X, and the hypothesis that CH0 of X omega is Z is equivalent to the fact that there exists a positive integer n and a point X in X of C, such that n times the diagonal is rationally equivalent to Z1 plus Z2 in the Chow group of codimension D on X cross X. The support of Z1 being in little x times capital X, and the support of Z2 being X cross Y, where Y is a proper closed set in X. And if you make this hypothesis, this is enough to imply that all the HI XOX are 0 for I at least 1. And other things. So, and this notion of universally CH0 trivial, which we had in the previous slide, is equivalent to this property with n equals 1. Okay, now there's a warning here, and it's, I mean, several people have come across this. I mean, in fact, it's been known for a while, but people rediscover it. That there exist surfaces of the complex which are universally CH0 trivial, which sounds like a very strong property, but nevertheless, they are of general type. Okay, so in particular, they're certainly not stable rational. So the differentials will tell you that they're not rational. And for these surfaces, what happens is that A0 of xk indeed is 0, but A0, well, for some of these examples, you find A0 of x2k is non-zero. Okay, so let me, so I told you that we wanted to generalize the Brouwer group. So something which was, so in fact, in the talks by Grothendieck and the Brouwer group, he suggested a birational invariant and a higher dimension, which was you take X smooth and projective over, say, C, and you look at the image of HI etal of X, say, mod Zn, with values in HI the function field. And that's a rather small group. And there's a group which, in fact, is, well, I think more interesting, is the unified cohomology. So what is this? You take, so I'm going to take to Galois cohomology. I have a variety X smooth and projective over a field K, and an integer n which is prime to the characteristic, and I look at a subgroup of the Galois cohomology of the function field with coefficient mu n tensor j. I look at the classes which have the property that at any point of codimension 1 on your variety, the residue is trivial. So there's a notion of residue for discrete variation rings. And in fact, this group, which is defined in terms of a given smooth projective model, does not depend on the smooth projective model. So it's if you use Bloch-August, that is, if you use the Guston conjecture for Galois cohomology as proved by Bloch and August following I mean, mimicking what Quillen had done, you find that this group, which is defined in terms of model, can be defined purely in terms of the function field. You look at all the possible discrete variation rings of rank 1 in K of x, which are trivial and K, and you look at all the possible residues. And it's quite useful to have this definition because in concrete examples, all the varieties are singular. Okay? So it's very hard to find a smooth projective model. So these are K birational invariants, they're even stably K birational invariant. And when they're retract rational, when the variety is retract rational, you can prove that the unified cohomology is just reduced to the cohomology of the ground field, which is the obvious part of it. Something I'd use at some point is if you have two different algebraically closed fields, K and K, the unified cohomology with torsion coefficients doesn't change when you change the ground field. And this is special. This is this rigidity theorems of Suslin, which were generalized. Okay. So it's very nice to define things, but the problem is to use them. Okay? So for the time being, let me simply say, suppose X is smooth and projective. If it is retract rational, then as I said, it's universally CH0 trivial, meaning that over any overfield F of your ground field K, CH0 of X index F is just Z by the degree map. And then this implies that for any overfield of K, any I, any N, the unified cohomology is reduced to the bottom cohomology. I mean, this is not very hard to prove. So this is weaker than universally CH0 trivial. But at the same time, you might hope that in some concrete cases, it's easier to compute some non-trivial element in the unified cohomology. So just to illustrate what these groups are in low dimension. So for H1, the unified H1 is simply H1 eta like Q mod Z. And for K equals C, you know that this group is an extension of the two torsion part in the Betti cohomology at level 2 by Q mod Z to the power B1. And the defect is rationally connected, and in fact pi 1x is 0. So you're not going to use it. Okay? It's useless for this case. If K is 2, then what we find is exactly the Brauer group. And for K equals C, so this is something you can read in Grothendieck's papers, the Brauer group. This group is an extension of the finite group, the three torsion in Betti, which we had before, by Q mod Z to the power B2 minus rho. And the reason this B2 minus rho didn't appear in what I mentioned about the Pottenhoff invariant is that if you stick to rationally connected varieties, well, that's 0. So it's just this part which might exist for rationally connected varieties. Okay, now, what about H3? So Clavoisin and I, we discussed at some point, because she had some birational invariants, and I knew some birational invariants, and there was a question of whether there is a connection between these two. The funny thing is that birational invariants, she shows it, there are birational invariants by using the technique of, well, Hironaka, and the fact that you discuss what happens in the blow-up of a smooth subvariety. Whereas the other birational invariants, a la Bloch-August, you invoke the custom conjecture to show that the thing is birational invariant. So it's really quite different method. It's quite striking. So anyway, so what Clavoisin has investigated a lot is the integral Hodge conjecture. So you look at the cycles, you have a map from CH2 of x to H4 Betti xz, and in H4 x Betti xz, you look at the classes which are Hodge when you tensor with Q. Okay. And then you look at the quotient. So the Hodge conjecture, a special case of the Hodge conjecture, says that this group should be finite. And then everybody says, oh, and then everybody knows that the Hodge conjecture is false with integral coefficient, and you stop thinking. But well, you might try to think a bit. And so, so what we proved is that for any smooth projective variety over the complex, the unified cohomology group H3NR f of x over f q mod z of 2, I see there's a mistake here. This is C, of course. This is computed over C. Is an extension of the finite group Z4 torsion, which you can define. I mean, conjecture is Z4 of x, but you can look at it anyway, by the divisible group. Okay? And then in the special case when the CH0 of x is Z, for instance, X is rationally connected, which are the varieties of interest in this lecture anyway, then Z4 of X actually is finite, and then these two invariants coincide. Okay, so H3 unified for a rationally connected variety, H3 unified of the function field of X is just the defect of the integral Hodge conjecture for cycles of connection 2. No. This is no. In this particular case, if it's rationally connected, then in fact this group is torsion. Above, no, I put the torsion. So you can always consider this group. You know, it's just. No, this one is finite. This one is finite. Because it's no. I mean, this thing is a finite type anyway. Okay, and so Voisin proved that for rationally connected varieties of dimension 3, that 4 of X actually is 0. Okay, so this implies that this unverified cohomology group is going to be of no use to detect non-rationality of rationally connected threefolds. And in a higher dimension, so this was the point where we met, is that in fact there exist examples of projective unirational varieties of dimension at least 6 where the prob of X is 0, but the unified cohomology is non-trivial. This is something I did with Oyongoren quite a few years back, and this used method from algebraic K-theory. Well, actually, it uses the result of Arason and quartic forms, which was a predecessor of Markov-Thélène. It's this kind of results where typically Witt proved that if you take a conic over a field, the kernel from the prob of K to the prob of the function field of the conic is just Z mod 2 spanned by the class of the quaternary associated to the conic. And what Arason proved was a similar result if you take a Pfister form and you look at the corresponding D-fold Pfister form, and you look at HD. Actually, he was looking at a threefold Pfister form instead of twofold Pfister form, which was the Witt case. And you look at H3 of K with coefficient Z mod 2 goes to H3 of the function field of that threefold Pfister form, the quartic associated to this, and he showed that the kernel was just Z mod 2 spanned by the obvious cup product A cup B cup C if you're diagonal. Okay, so we were using this to get the. So this is a method where you prove that this group is non-zero without actually constructing a smooth projective model. And so you use the partial definition with all the possible discrete Variation rings. Okay, so the conclusion is that there are rationally connected varieties of any dimension at least 6 for which the integral Hodge conjecture fails for codimension 2 cycles. And in dimensions 4 and 5, the question is open. Okay, now let me show you a new, what is new? Nothing is new. A stable partial invariant. You take a smooth projective variety, and you take an overfield of C, an algebraic closure of F, G is the Carter group of F bar over F. And I claim that if you look at the co-kernel of Chow group of codimension 2 and XF to Chow group of codimension 2 and F bar invariant by Galois, this is a partial invariant trivial on stably rational varieties. So the proof is not difficult. It's just once you've said it, you can see the proof. The proof is the behavior of Chow group on the blow up of smooth varieties. So when you blow up, you add a pick of something. Okay. And so the difference between the two will be the map from pick YF to pick YF bar invariant by G. Now, now in this particular case, because I start with blobs which are defined over C, the variety Y automatically has a point. So this natural map here is onto whatever field I consider over this one. So I couldn't have written a similar result starting from a variety of arbitrary field. I would have been stuck there. So this partial invariant, in some cases of interest here, is related to the previous invariance. And so here is something which follows from techniques developed by Spencer Bloch and then Wayne Raskin and I, and then Bruno Kahn. So assume the variety for which over C, for which the Chow group of a C is trivial. It's just reduced to the degree map. And you assume that the first invariants that might tell you that the variety is not rational are 0. Okay, so you assume that H2 XZ torsion is 0, H3 XZ torsion is 0, and you assume that the H3 unified at the level of C is 0. So this has failed. then if you take any field over C, there is an exact sequence which involves H305 f of x divided by the constant part, the invariant I just mentioned, and then there's a map which actually is quite mysterious. I don't know how to compute it, to H2 Galois with values in peak x f bar tensed over Z with f bar star. So this is a lattice in our setup. Okay, so this is just a torus. Okay. So anyway, it connects the two invariants. And so, in fact, I got involved in this topic because there was an AIN meeting. So for those of you who haven't been there, AIN is a place where you feel you go back to school because they put you in a room and they say, try to get some idea, try to some project. Okay, so so there was a project. So I mean, the French tend to consider this as quite ridiculous, but in fact, sometimes it works. So we were trying to use unified cohomology H3 to try to decide that if we take objects which we understand, what we think we understand, namely cubic hypersurfaces in P5 which contain a P2, because now you can fiber them into quartics over P2 and you feel more comfortable. So we're trying to compute H305 for the universal H305 for these things and hoping that this might not be zero. Fortunately, what we proved is that if we take a very general smooth cubic hypersurface in P5 containing a plane, for any field F containing C, this unified cohomology is constant. Okay, so we were using this fibration, which I just mentioned, okay, plus the fact that the cohomology of the unified cohomology of quartics has been computed by Khan, Ross, and Sujata. But that result very quickly was superseded by Clavoisin, who proved that if you take any smooth projective cubic hypersurface in P5, for any field F containing C, the unified cohomology, in fact, is trivial. It's reduced to the constant part. So I'm going to try to give a partially alternative proof of our result. So I got interested in the result, and I find it very hard to read what she writes, so I tried to prove it in a different manner. So, no offense. So, in fact, for the time being, we have to use something she proved, namely that over the complex, the H305 is trivial. So she proved the integral hot conjecture for conversion 2 cycles on cubic fourfolds, which by this theorem we put together implies H305 C of x over C is 0. Okay. Now, by this rigidity result I mentioned, due to Janssen, for instance, even over F bar, this is still true. Okay. And then we look at the slides we had there. So we're applying this, the fact that H305 is, so we can compare the two slides here. So what we get is that the H305 f of x modulo the constant part is a subgroup of the co-column of CH2 of x f goes to CH2 of fx bar g. Okay. But now if you look at codimension 2 cycles on this 4-dimensional cubic, in fact they are sort of dull. There's no intermediate Jacobian at that level. And so the algebraic, rational equivalence, algebraic equivalence, homological all coincide. So the thing is completely, I don't say rigid. Yeah? So the map from CH2 of x to CH2 of x bar is an isomorphism. It doesn't change when you change the algebraically closed field. And this trivially implies that the map from CH2 of xf to CH2 of x bar g is onto. Okay, so that's 0, and therefore this one is 0. And I think it's it would be interesting to compare the different proofs. Any comment? I mean, this is not exactly my field, so if there's something wrong, tell me.
Justify that by saying the intermediate Jacobian dashes.
Yeah.
It's an indication that the four-dimension 2 cycles non-rational equivalence should be the same as modulo homological equivalence. But how do you see that?
I don't know. Yeah, it's true, but it's true. I'm quite at a loss to answer this question right away. What are you saying? Okay. When? Okay. Yeah, you can tell me more about it. Okay, and so in fact, again, we saw that H305 is trivial, so there's no way to tell that the thing is not rational by using this method. And in fact, the situation is even worse because in recent work, one has produced families of cubic fourfolds in P5C for which C0 of x is universally trivial. So we don't know.
But there are also some which are rational, right? So the point is.
Yeah, but not she's okay, and not quite a few. I don't want to go into the description of which quite a few. You're quite, absolutely. Okay, so let's stay, just before I go to the specialization method, so let's discuss smooth cubic hypersurfaces in P4C for a minute from this point of view. So in this case, for any such cubic hypersurfaces, one can show that the two sides are the same. Remember, I had an exact sequence, H305 modulo H3, this co-kernel, and then there was this Miss-Zeroff map into H2 G peak X F bar tensor F bar star. And in that case, one manages to get rid of it by using the functority of the sequence and reducing to something of lower dimension lying inside the cubic hypersurface. So one really has an isomorphism here. So the question is whether this group can be non-zero for threefold this time. Okay. And which of course would be great because it would show that X is not severely rational. So the key case is when F is a function field of an intimate Jacobian again, which is an abelian variety, parametrizing cycles of condition 2 which are homologous to 0. And then you have an obvious class in H2 of X bar, XF bar G, which correspond to the fact that this parameterizes cycles of condition 2 over an algebraically closed field. So you take the difference between this class and maybe the class of a trivial element. And then you ask whether this comes from a class in CH2 of XF, okay, which would define a universal convention 2 cycle. XF is just X cross, it's X, you look at X cross the Jacobian, and you restrict to the joint point of the Jacobian. Okay. So at least one can see that there's a connection between this question of having a universal convention 2 cycle and the vanishing of the thing on the left. And so by, in fact, not by this case-theoretic method, but by a bit different method, Clairvoyant in fact has proved that the existence of universal convention 2 cycle on X is equivalent to this vanishing for any field F. So possibly she'll say something about this later. And okay, for cubic surfaces, hypersurfaces in P4, the mystery remains, of course. But at least she found examples of rationally conjugated threefolds for which this group is not zero. Okay. So you could think for a minute, okay, that's great. That's the first application of H305. But in fact, the way she gets it, as far as I understand what she does, the proof relies on the special arguments which we're going to discuss, which she introduced. And then afterwards, she can show that for this thing, which is double cover, which is a double cover of P3 ramified along a general quartic surface with 7 nodes, this group is non-zero for suitable F. Okay. So I think now I get to the non-rationality by special arguments. So, an unequal characteristic, a specialization method to prove non-rooledness, based on a result of an old result of Matsuzaka, was used by Kolar in 1995. And it was quite spectacular because he proved that basically 1/3 of the Fano hypersurfaces, general Fano hypersurfaces of a C, are not ruled. Now, in equal characteristic 0, I mean, we are over discrete Variation ring, so I'm talking about the characteristic of the fraction field is say 0, and the characteristic of the radius field is positive or 0. So in equal characteristic 0, a different method was used not such a long time ago by Clairvoyant. So she used the action of correspondences and Chow groups and on Betty homology, and she will describe this in her talk. Especially the emphasis on the decomposition of the diagonal aspect, which is more geometric than the point of view of universal triviality of Chow groups. And a variant of the method was produced and applied by Pirotka and me. And we used in a very direct fashion the specialization map defined by Fulton and the Chow group 0 cycles when you're over the field of fraction of a DVR. I'll come to that. This is just the introduction. So let me be very brief about what Clara has done because she's saying more about it. Yeah. So she considers a double cover of P3 ramifying along a quartic surface in P3. And then she proves that if the surface has at most 7 ordinary singularities and is otherwise very general means outside the countable, you look at the parameter space of your object, which is some projective space, and you take away a countable union of proper subvarieties, and then you take a point in the complement. So you're over C, and because you want a point outside. I mean, you could consider it over any field, but there might be no point. Okay, if it's otherwise very general, then X is not stably rational, but it's satisfied that bar above X is 0, and the unramified H3 is 0. Okay. But nevertheless, so these invariants fail, but she managed to prove that X is not stably rational. And the method is by specializing to an Artin-Mumford threefold, which has 10 nodes rather than 7. Okay. And this is what I write here. This is a double cover P3 ramified along a suitable quartic surface with 10 singularities. And as I said, Artin and Mumford produce such a Y with a desingularization Z satisfying bar of Z non-zero. So the specialization theorem we proved with Pirotka is the following. So you start with a discrete variation ring. The field of fraction is capital K, the radius field is little k, and let's assume it's algebraically closed for this statement. And you take a flat projective scheme over A, integral. Okay. You assume that the generic geometric fiber is smooth integral and universally CH0 trivial. So I repeat, universally CH0 trivial means over an overfield, CH0 of XF is just Z. The special fiber you assume is integral, and you assume that there's a discrimination morphism, Z to Y, as we had before, which is universally CH0 trivial. So what does that mean? It means that if you take any overfield of your ground field, the projection map from CH0 ZF to CH0 YF is an isomorphism. And then the conclusion is that Z is universally CH0 trivial. So if the generic fiber was, geometric generic fiber was universally CH0 trivial, if the desingularization of the special fiber, the morphism of desingularization is a universal CH0 isomorphism, then the desingularized map variety on the special fiber is universally CH0 trivial. So in particular, the bar of Z is going to be 0. Okay, so here's the proof. So maybe shy. Okay, so let me slowly go through it. So the point is, you reduce to the case where the discrete variation ring is a complete DVR with you field F. So we started with little k. You started with little k. We have k here and a here. And you want to show that you want to deduce that that CH0. You want to show that CH0 of ZF is 0, is Z. Okay. So, well, I mean, you find some DVR above A with fraction field F. Okay. And I mean, at the beginning we hadn't tried Bourbaki, so we thought we first did that in an easy case. But in fact, there's something called le gonflement des anneaux locaux in Bourbaki, which tells you how to do it. It's quite easy. So you find a DVR here, and then you complete. Because anyway, for the result which you want, you can complete. Okay? So you get a situation at that level. Okay. And now you have an open set in Y, which is isomorphic to P minus, so the projection for P minus 1 of U to U is an isomorphism. Okay? So set V equals P minus U. Then you take a zero cycle of degree 0 on Z. Remember, Z is the dimensionalization. So this is U here, this is P minus 1 of U, which we'll call V, sorry. This one is an isomorphism. So what you do is that you take your zero cycle, and again you use the moving lemma to push it into a zero cycle with support in V. And you push it down to U, and then because you're smooth, and this part, U is smooth, Q smooth. And you're over this complete DVR, you can lift the zero cycle to the generic fiber. So U smooth and A is complete. You can lift the zero cycle to one cycle of relative degree 0. And then you use the fact proved by Fulton that the homomorphism CH low 1 of X to CH0Y induces a homomorphism from CH0 of the generic fiber to CH0 of the special fiber. And that's the theorem which is proved without any smoothness assumption on the morphism. And then, since you assume that CH0 of X was universally trivial, so in particular over K, there's a K, well, I'm guessing over K, we already did the reduction, then you deduce that the specializing thing is 0 here. But because you assume that on the distribution level, the map P low star was an homomorphism, you conclude that your cycle was 0 upstairs. So it's really quite simple. So it builds exactly, I mean, the whole point is this result, which is not entirely true. Now, if you don't like this result, in fact, there's a way to prove the same results by using R equivalence. So it's in fact quite easy to show that R equivalence is an equivalence relation on of rational points of projective varieties. You see that 2 points are R equivalent, 2 rational points are R equivalent. If there's a morphism from P1 ground field to your variety, such that the 2 points are in the image of rational points in P1. And you take, of course, it's not a equivalence relation, you take the equivalence relation generated by this. And it's quite easy to show that this R equivalence property, if you're over DVR, it specializes. Basically, because when you take P1A and you blow up, you just get chains of P1. That's a quick proof. And then for our purposes of proving the special argument, it would just work the same. Okay. So I repeat, we do not impose any irregularity condition on the total space. So in particular, this is quite, in fact, it's quite useful in the proof, because when you make this change, A goes to B, horrible things happen to your total space X, but you don't care. And one doesn't even assume that that the generic fiber is smooth. So I guess I assumed it in the statement, but one can do it. So here I say what the generic fiber is smooth. Okay. Now in fact one can replace this by the generic fiber, geometric generic fiber, has a desingularization with the property that it is CH0 universally trivial. So I mean we can do more general result than this one. This is what I meant here. I mean, we don't have a concrete application right now, but it's good to know. Okay. So hypothesis and special fiber. So there's this hypothesis that the discrimination morphism is universally CH0 trivial. Now, one remark is that this is a property which depends only on Y. Okay, second thing is, and which is quite useful in applications, you want to show that your map is universally CH0 trivial. Here's a criterion. For any schematic point of Y with the field kappa of M, the fiber is universally CH0 trivial. That's enough. So to check that the morphism on the total space P low star is a universal CH0 isomorphism, it's enough to check it on all the fibers. Same statement on all fibers. And a simple example for a universally CH0 trivial morphism Z to Y is you take Kirchberger close, dimension of Y at least 2, that's important, and all singularities of y are ordinary quartic singularities, which was the example which Lev was used at the beginning. Okay, now we come to the examples which we want to produce to get at quartic hypersurfaces in P4. So we're going to give two examples of that kind. So we want Z desingularization to satisfy the homomorphism Z to Y is interested CH0 trivial. And then we'd like the bar of Z to be non-zero, because ultimately we want to show that the quartic is not stably rational. Okay, so we want either of these properties which are equivalent. So one starts with an Artin-Mumford surface in P3C. So an Artin-Mumford surface is given by an equation like this, where alpha 2 is of degree 2, beta 3 of degree 3, gamma 4 is of degree 4. And then beta square minus alpha gamma is the product of two cubic forms corresponding to ellipticals in P2C, which have a common conic tangent to each of them. So the conic is tritangent to each elliptic curve. That's the example they produce. Okay, and start with this, and then when one can push this into a quartic. So in fact, we came across this idea because we saw a paper of Jun Hu, who was doing a computation like this for a singular quartic given by an equation like this. So to the original thing, you add Z4 squared times a conic, okay, and a smooth conic. So he constructed a desingularization of Y, called in his paper an L desingularization, which I understand is something in the same spirit as CH0's trivial, CH0 trivial desingularization. And then so he has this new variety. He computes the torsion and then finds not zero. So that's just as Artin-Mumford had done. And Turika and I, we proposed another example, which involves less work. Namely, we put something Z no square instead of delta 2, Z0, Z1, and singular. And we computed a desingularization. Now there's some work which has to be done. And we show that by this criterion that it is universally CH0 trivial. But then we don't have to worry about the torsion, because that thing is birational to the Artin-Mumford double cover. So they've already computed that the log of a smooth projective model is non-zero. So for the lazy people, it's better. But there's still some work. You have to compute the desingularization and then see that the fibers are conics or quadratic or whatever, and then something for which you know that which are universally CH0 trivial. So the singularities are not isolated. That's the point. Okay, so if you get a line of singularities. So now you can take these singular quartics with coefficients in Q bar. And now if you take the projective space parameterizing quartics in P4, and you take a line defined over Q bar, which is not contained in the locus of singular quartics in P4, and you take and which goes through the specific point we looked at, then the conclusion is if you take any point in L of C which doesn't belong to, if you take any point in L of C which doesn't belong to L of Q bar, and you use the specialization method, well, you get that the corresponding quartic geometrically is not stably rational. So you produce quartic hypersurfaces defined of algebraic closure of Q of T, which are not retract rational, which is well, for some people it's a bit better than outside the countable union of hypersurfaces in P and C. And so this is compared with the Iskowski-Manin result that no smooth quartic in P4C is rational. So, okay, this Q of T bar is constant. In fact, one can do better. This was suggested to us by Wittenberg. There are smooth quartic hypersurfaces defined over Q bar, not only over Q of T bar, which are not retract rational. And so what you do is you use the specialization method over DVR to reduce to a finite field, basically. I mean, it's an extension of a finite field. So you start with a singular quartic over P4 Q bar, as we had. Okay. And then this thing exists. You can spread it out over an open set of the ring of integers in some finite extension of Q. Okay. And And then the resolution you have there, of course, you get it over an open set of your ring of integers. And then you want to control the Brouwer group. But because the Brouwer group is basically, in this case, is just the two torsion in the étale homology with coefficients Z2. It's in the geometric fibers, it doesn't move. So you also know it's going to be non-zero there. And so, well, that's a proof. Yeah. So there's been further work. I mean, this, at least this is a topic where people are interested. so Bouville used the specialized argument to show that double covers of P4C and P5C ramified along a very general quartic hypersurface are not stably rational, in fact, not retract rational. And he also showed that double covers of P3 ramified along a very general sextic surface are not retract rational. So his specialization is to characteristic 0. And so he knows this, the geometry of the situation very well. I mean, he computes the desingularization and also computes that there's a non-trivial element in H3 XZ torsion. H3 ZZ torsion with my notation. And then very recently, just 3 weeks before this conference, Totaro has pushed the method to get very impressive results. He showed that some very close analog, even a bit better, of the results which Collar got 20 years ago. So it shows that if you take any integers, I'm very bad, I don't know how to write the roof in text, so, so if you take any integers d and n at least 3, for which the d mod 2 is, you can switch to an integer between d mod 2 and this quantity here, then the very general hypersurface of degree in Pn is not retract rational. So this includes quartic fourfolds, for which rationality was not even known. And so his method is, do I see something in the next one? Yeah. So he uses the specialization method in unequal characteristic, more precisely to characteristic 2. And for hypersurface of even degree, he reduces the varieties Y with a very simple result. They are a priori they're a bit frightening because the double covers of something in characteristic 2 and but anyway, but they have a very simple resolution of singularities, Z, with the property that for some I, which actually is I think the dimension of Z minus 1, the global sections of Z of omega I are non-zero. This is something which Collar, in fact, Collar had studied, had used, in fact, this specialization in the result, in the 20 years old results which I mentioned. And so this is what I'm saying. And then Totaro notes that the distance of Z to Y is a universal C0 isomorphism. And then he uses a cycle map defined by Gros combined with an argument of Bloch's universe style to prove that, in fact, this Z is not universally C0 trivial. So is it a correct summary? Okay, so I have 5 minutes for the appendix, which is okay. So I know the ground field here is C, so maybe some people will disapprove of this, but smooth cubic hypersurfaces in P and K over a non-algebraic closed field. So you can stop listening if you want. So there exist cubic surfaces in P3 with Brouwer of X different from Brouwer of K, and it's in particular not retract rational. And in fact, this is somehow, for me, this is the beginning of the story, because a long time ago, Shafarich and Manin were discussing cubic surfaces of a non-algebraic closed field and computing the Brouwer of X. So it's been known for a long time that these things are not retract rational. You can do it over a C of T, you can do it even over a finite field. So typically if you take x cubed plus y cubed plus z cubed plus at cubed over a field of characteristics different from 3 and a is not a cube, this thing is not retract rational. A equals 0. Okay. There exist also cubic smooth cubic surfaces in P3Q, which are stably rational over Q, which are not rational over Q. In fact, this already exists over QP, and this is the same argument as we used in the paper with Bouville, Sansukenson, and Naya. So you consider universal torses, and you show that in fact they are rational in the case when the anyway. I don't want to mention something which is easy is to, over the reals to find cubic hypersurfaces which are such that the real locus, or the locus of real point, is not connected. So you do it by deformation of, take an equation like this, which is singular, but all the real points are non-singular, and then you deform, and that's enough. And in that case, one can show that, well, first of all, it's quite obvious that it's not going to be rational, at least. Retract rational, we'll have to think a bit more, I think, for retract rational. It's not completely obvious that, well, yes, I think it's obvious, because you would do the same argument connecting 2 points by something connected and going through Pn. But in any case, well, there's a general result about this kind of thing, so you can show that the group of 0 cycles of degree 0 modulo rational comes to Z mod 2 in that case. So these are not stably rational. And that you can get in any dimension, at least. This is the only case which I know. And now, let's look at the field of Colliot dimension 2. So, over the field C double parenthesis X, double parenthesis Y, one can produce such cubic hypersurfaces which are not stably rational. When actually use a partial model and compute that the Chow group of 0 cycles is not 0. This, and now using the method of our paper with Pirutka, in fact in the paper with Pirutka, we proved that, so the problem was that if you wanted to do something like this over a usual local field, you could say C double plus X is just like a finite field. It doesn't work, because in the argument here, at the end, we have a principal homogeneous space of an abelian variety of a C double plus X, which is not trivial. But over a finite field, they would be trivial, so the argument would fail at that point. So that's why it's interesting to, well, it's a challenge to see whether you can do that over QP. And so to make things simple, suppose you have something like this with a cubic extension, which is unramified of QP, and you look at this equation. So you take the norm for this cubic extension, you add this, and then you put some decent form phi with coefficient ZP, and put a P here, and then you can show that this cubic hypersurface, which is non-singular, is not retract rational by using the specialization technique in the paper. And in fact, it was a bit difficult so you have to check at the end. So you look at the special fiber, you resolve the singularities. It's not too hard. But the thing which was not completely obvious was to see that the Bra group of this variety over a finite field was not trivial. So there was a computation there which we did. Okay, and so let me conclude 1 minute with the open problems. So in all these cases, I have no idea whether there exists a smooth cubic hypersurface which is not stably rational. So over C, this is a problem. Over C double parenthesis T or C parenthesis T. Over a finite field, as soon as n is at least 4. Over that field, as soon as n is at least 5. Over QP, as soon as n is at least 5. I don't know whether there exists such a cubic hypersurface which are not stably rational. And this is exactly the end of the talk.